Okay, law of conservation of energy is the next topic, which kind of brings all the kinetic and potential energy together. The definition of that is energy is neither created nor destroyed. Now, if you think about that statement, that means that the entire universe has X amount of energy, and because we can't destroy it or create it, it's not going to be any more, it's not going to be any less. It is a finite quantity of energy, although the word finite generally means you have an amount you can measure. We can't measure all the energy in the universe, but whatever it is, we can't change it. We can just change it into different forms. And that's what this is all about. Now, the two types of energy that we do deal with are kinetic and potential energy. Now, there are other forms of energy, but the two types are kinetic and potential. Energy stored or getting ready to be created, or energy in motion. Those are the two main ones. And so that means every system, whatever it is, whether it's me dropping this pen or something else, is going to have the same amount of energy within that system, whatever that system means. So that means that the amount of potential and kinetic energy together has to be the same, no matter what, in that particular system. Now, you change the system, you change the amount of energy in that system, but we never change the total amount of energy in the universe. Take this example, 35-gram rock is dropped from a cliff at 50 meters high. Okay? We have 35-gram rock, so that means that's the mass, and height of 50 meters. So, if we're holding it up here, there is no motion involved outside of the fact that we're moving about 1,000 miles per hour around the center of the Earth, but regardless, in relative terms, it's not moving, and then when we drop it, it's going to move 1,000 miles per hour in that direction, the same direction that we're driving. So, that's not going to be part of the calculation. The system is the actual dropping of the pen. So, that means potential energy is going to be all there is, meaning then that kinetic energy is 0, or 0 joules. There is no kinetic energy. So the total is just going to be the potential energy since 0 is being added to it. Well, how do we find potential energy? MGH. So it's 0.0350 kilograms. Because in energy, mass must be expressed in kilograms, times gravitational acceleration, 9.80 meters per second squared, times the distance, which is 50 meters. Okay, and so we go look at that answer there, and we find that it is 17.2 joules. So that means the total energy will be that quantity since this is 0, 17.2 joules. But as the pen is dropped, it's going to be gaining velocity because it's accelerating, which means it's going to be gaining kinetic energy and losing potential energy, with the sum at each point in time is going to be 17.2 joules. So let's take another situation. Same situation. Only we want to know now what are the kinetic potential energies after the rock has dropped for 1.5 seconds. And there's two ways that we can do this. We can take a look at the rock after it's dropped 1.5 seconds in terms of either velocity or kinetic energy, or height in terms of potential energy. So let's take that 1.50 seconds. Let's find out how far it dropped. Now, this is kind of tricky. This is where people mess this up. When you find the value for D, it's not the D from the ground up to that, it's from where you dropped it down to that. So you're going to have to subtract from 50 whatever you find here. Alright, so the height, or the loss of height, is going to be distance is 1/2 AT squared. Okay, so this is going to be equal to 0.5 times 9.80, doing math in my head here, 9.80 meters per second squared times 1.50 seconds squared. All right, you look for that answer right there. You find that that is 11 meters. So it's going to drop 11 meters. That means then that the new height, we call that h prime, because our like primes, 50 meters times 11 meters is 39 meters. So that is the height that we're actually going to deal with now. So we go back to mgh, which is your potential energy. And so that's going to be 0.035 kilograms times the 9.80 meters per second squared times this new height of 39 meters. Okay, I'll do this in my head, shall we? No, I won't. I can't do that. Even though I've done it already once. It turns out that that is going to be 13.4 joules. Now the kinetic energy is such that the total energy is equal to the potential energy plus the kinetic energy. Well, the total energy we said is 17.2 joules. The potential energy is 13.4 joules. And the kinetic energy then is going to be the difference between these two. And that's going to give us then kinetic energy of 3.8 joules. Now that's one way of doing it. Another way of doing it is by solving for EK first. So we go back to that 1.5 seconds. And now we want to find the velocity, or the final velocity, because the initial velocity is 0, by using the formula delta V equals A times T. Well, delta V is VF minus VI, VI is 0, so that drops out. So that gives us this. And this is going to be 9.80 meters per second squared times the time, which is 1.5 seconds. And this is going to give us a velocity at that point of 14.7 meters per second. So the kinetic energy is defined as 1/2 mv squared. And this is going to be 1/2 or 0.5 times the mass, which is 0.0350 kilograms, times this velocity, 14.7 meters per second, whole thing being squared. And it turns out that this is going to be, I believe, 3.78 joules, which is about the 3.8 we got. In fact, we couldn't go past the first decimal place in the other problem because we had measurements that only went one decimal place. So this probably would have been exactly the same as the other one. But regardless, and again, E total equals potential energy plus the kinetic energy. And so that's going to be 17.2 joules is equal to potential energy, which is what we're going to solve for, plus the kinetic is 3.78 joules. Subtract that, and our potential energy then becomes 13.4 joules, which I believe is what we got last time. Okay? All right, so that's the kind of mathematical manipulation we're going to have to do for this section. And so the practice problems is you're going to have basically a 16-pound bowling ball. It's dropped from the top of a 225-meter building, and who doesn't want to do that? And the questions here is, what are the potential kinetic energy under these 5 scenarios? Force drop, 3.5 seconds after it's dropped, halfway down, after dropping for 175 meters, and then just before it makes contact with the pavement. Okay? Have fun.